I want to make this short video to kind of go over some hints and some of the examples from the homework and the review over the optimization. I know these are sometimes hard to understand. And what we're looking for is we are looking for max and mins. And remember, we really have two different ways we can find max and mins, right? One way to find max and mins is the first derivative test, and that is where we want to do sign analysis. And we do sign analysis with the first derivative, and then that tells us decreasing, increasing, decreasing, and we can determine our max and mins. For our second derivative test, we find the second derivative and we put our two critical points into the second derivative. And if we have a minimum, like at A here, then this second derivative is going to be greater than 0. If we have a maximum, like we do at B, our second derivative will be less than 0. So here it's positive, here it's negative. So let's look at a couple examples. So let's say we have this function, 1/3 x cubed minus 1/2 x squared plus 7. So we find the derivative, and this is x squared minus x, which tells us this is x minus 1. So my two critical points are 0 and 1. Now, if we need to determine where it's increasing, where it's decreasing, and all that other kind of stuff, we could go to sign analysis. But if we don't need to do sign analysis, if all we have to do is determine max and mins, sometimes it's easier just to do second derivative. And then we put in 0 into the second derivative, which gives us -1. We put 1 into the second derivative, which gives us 1. And if our second derivative is negative at 0, that tells us this is less than 0, and that tells us that is a max. Here 1 is greater than 0, that tells us it's a min. So we don't have to do sign analysis. And this really is important in a way you can do this when there's this review problem on the review that talks about velocity of a rocket is given, find the extreme value. Well, if we take our derivative, we get 2ax minus b. So if we find our critical point when we set this equal to 0, this is 2ax equals b, and we divide by 2a, and we get b over 2a. So that is our critical point. So that's that could be our max or a min, but we have to check. So to check, we find our second derivative, and our second derivative is just 2a. You'll notice there's no x, so we don't have to substitute this back in at all to find it. We just know this is 2a is greater than 0. It tells us a is positive. That tells us that is a min. So we know we have a minimum at x equals b over 2a. So we're using the second derivative test. We don't have to do sign analysis. Now, from the homework, there was some where you do have to do sign analysis. So let's look at this one. Once again, the first thing on these kind of problems is you want to think about what is the variable. What are you solving for? What's the variable? In this case, it's capital N. So if we want to find our two critical points, that is the bottom's always positive, so it's this n squared minus 1 is the only part that has to be 0, so that gets us plus or minus 1 is our critical points. Now in this point, I don't really want to take the second derivative of this. And the last one, it was very easy to find the second derivative, so I just did the second derivative test. Here, it's not easy to find the second derivative. So in this case, I am going to do sign analysis. Now, as I look at this and I do this sign analysis, the bottom of this is always positive. That doesn't matter. Okay? So I'm only doing sign analysis on the top. Okay? And for this one, let me, if you think of doing sign analysis here on the top, you would think if we just look at the n squared minus 1 part, that would just be like this. So we would have plus minus plus. However, we have this minus k in front, which what that does is that changes the sign of everything. And where this little simple n squared minus 1 quadratic parabola is plus minus plus, the negative in k out in front changes it, so it becomes a minus plus minus. And now negative positive, this is a min, positive negative, this is a max. And so the question is, where is the best nitrogen level for the best yield? And that's going to be at a maximum when n equals 1. And the last one I want to look at is probably one of the hardest ones, just because the equation is hard to solve and deal with. So we have this. Once again, first thing we have to decide, what is the variable? You have mu, you have w, you have sines and cosines. What is our variable? And our variable is our theta. It is our angle. So if we look at our derivative over here, the bottom is squared, so that's always positive, so we're okay. We know that this mu is a constant. We know this w is a constant with a constant weight, so those are not necessarily zero. So really, we have to look at this one thing. We want to determine for our critical point, where is mu cosine of theta minus sine equal to 0. Well, if you add over the sine and then divide by cosine, this just gives you mu is tangent of 0. And if you're solving for theta, remember, theta is our variable. Theta is what we're solving for. Theta is just inverse tangent of mu. Now remember, this is just some angle. Theta is just some angle. And so this inverse tangent of mu is just some angle, right? So let's do our sine analysis. So we want to do our sine analysis of the first derivative, and our only critical point is this tangent, inverse tangent of mu. So how can we look and do our sine analysis? Well, if we look at the top here, look at our derivative, our bottom's always positive. This minus mu w is negative. So we know, if we think about down here, our bottom is always positive. We have this negative out in front, and then we have mu cosine of theta minus sine. So when we do our sine analysis, it's really going to come down to this right here. Now, if you remember from up here, we took that and we set it equal to 0. So that is really mu was equal to tangent of theta. Okay. Which, tell you what, let's not look at it that way. Let's look at it a different way. So let me approach it this way. Maybe this will help. If this right here is negative, then this whole thing, negative times a positive, is positive. If this is positive, then this whole thing is negative. So another way to look at it, if this mu cosine minus sine, if that is positive, that leads to the derivative being negative, right? Because if this is positive, positive times a negative divided by a positive. Now, if this is negative, and that's a negative, now negative, negative, positive, and that would lead to this being positive. So what we can see is depending on how this works out will tell us if this is positive or negative. It all comes down to this one part. We know everything else. It comes down to this one part. So if this has to be positive, this would tell us that mu, doing the same thing, bring the sine over, divide by cosine, mu has to be greater than that, right? Which would tell us that if sigma, once again, do the inverse, we get to there, just like we did up top. So that tells us if theta is less than this, our derivative is negative. Well, here's this value. If we are less than that value, this is negative. We could do the same thing over here, and we would get mu is less than tangent of theta, which tells us that tangent of mu is right there. So this tells us if our angle is greater than the inverse of mu, this is positive. So if we are greater than inverse of mu, this is positive. Now we see we have a negative and a positive. That tells us that this right here is a minimum. So as you look at these, here's what you want to focus on. If you have something like this, you're finding your critical point, and if it's easy to take the second derivative, then just do the second derivative to determine if it's max or min. Sometimes it's not easy to do the second derivative, and it's easier to just do sign analysis. And then sometimes, especially one like this one's not easy either way, but we definitely don't want to try to do the second derivative. But even the first derivative can be very hard. And the key when you're doing a hard one like this, back here it was realizing that, hey, we don't have to worry about the bottom. Always positive. We know this part always makes it negative. So it's just going to switch this easy part. That helps us. Over here, we realize that the bottom is always positive. This front part is always negative. So it all comes down to this one part, which is actually the same part we had to solve up here to find our critical point. So if you can narrow it down just to that piece that you needed to know, that can help. Hopefully this video helps with these two homework questions, this question off of the review, and kind of just an overview of the difference between first derivative and second derivative tests to find max and mins. On these optimization problems and all you're finding max or mins, you really have options. If you were doing a full problem where you need to find increasing, decreasing, concave, up or down, inflection points, max and mins, you were never going to use the second derivative test. That's just extra from what you're already finding. Hopefully this helps.